Okay. So no need to labor the chapter outline. That's just there for information. So the key differences between the ionic and the covalent bond are the ionic bond is a purely electrostatic attraction. In other words, electrons are transferred from one atom to the other and produces an imbalance of charge. And that the opposite charges then attract one another. And that's the sole force of attraction for an ionic bond. And I should say for a purely ionic bond. Whereas covalent bonds, well, and the ionic bond forms between a metal and a non-metal. All right, so you have this phone. Nine o'clock, everybody starts calling, all the junk calls. The ionic bond always forms between a metal and a non-metal, whereas a covalent bond forms between two non-metals. That's why the type 3 naming convention has to do with covalent bonds. What is a covalent bond? Well, as opposed to an ionic bond where electrons are transferred, in a covalent bond, the electrons are shared between the molecules. Between the atoms. And the primary reason for that is the strength of attraction for electrons between two non-metals is not strong enough to complete the charge. The electron is not completely transferred. It may spend a little more time on one side of the bond than the other, but neither side wins. So they reach a happy medium and just share the electrons. And what actually happens is the strength of the bond for a covalent bond is stronger than it is for an ionic bond. And we'll get into that a little bit more later. Now the ionic, let's see. Oh, there's Paul. Okay. The ionic bond forms, we write the compound as if it were individual ions, like sodium chloride. Right. That's the simplest whole number ratio of sodiums to chlorides. But in fact, in the structure, you see sodium ions and chloride ions grouped around one another. Then you'll have sodiums over here, sodiums over here. So it's really what we call a crystal lattice. And you'll have chlorides out here, and you have chlorides behind. So each one of those ions is surrounded by 6 others. So if we want to be truthful with our formulas, we'd actually have 6 and 6. But by convention, we go to the simplest ratio, which would be 1 to 1. Now that's for an ionic bonding situation. For covalent bonds, you have discrete molecules, we call them. In other words, when the bonds form, they're so strong that they isolate the bonded atoms together in discrete packages. So instead of being like this, water is like that, separate from all other water molecules. So when we say molecule, it's implied that the bonding is covalent. Okay, that is the basic structural unit of a covalently bonded unit. It's a molecule. Now, all ionic compounds are solids at room temperature. That's just the way they are. Whereas covalent compounds can either be solids, liquids, or gases, right? At room temperature and 1 atmosphere pressure, water is a liquid. But carbon dioxide is a gas. And there are some covalently bound compounds, like, see if I can think of one. Trying to think of a solid, a good example for a solid. Sulfur hexafluoride is a solid. And those are both nonmetals bound together. Okay, so you can have all three phases or possibilities for covalently bound atomic groups or molecules. Ionic solids, some of them are soluble in water. There's some that are not, but many that are. And when they do go into solution, they produce a conductive medium. They conduct electricity. So if you put sodium chloride in water and put 2 electrodes in it, then in the circuit, say you put a light bulb in there, the light bulb will turn on. If you put those same 2 electrodes in pure water, nothing happens. Pure water is an insulator. There are no ions in the solution to transfer the current from one side to the other. So when you have a solution like that with sodium ions and chloride ions, then when you put the electrodes in, and you have a light bulb, like that, then the light bulb turns on. But if this were pure water, like that, you have a dim light bulb. You need ions in here to complete the circuit. Well, when you dissolve covalently bound compounds, molecules, you don't get the light bulb doesn't turn on, because when they dissolve, they don't dissociate into ions. Now, that's usually the case. There are some covalently bound compounds that will slightly ionize. For instance, weak acids like acetic acid or vinegar. It will conduct electricity to dimly light the bulb. But most covalent compounds, when they go into solution, they don't dissociate, like sugar. If you put sucrose in water, the light bulb won't come on. Okay. So we have a covalent bond formed from 2 atoms that share electrons. Right? Here's an example. When you get 2 hydrogen atoms coming together, they each have 1 electron, right? But obviously, they both are the same element, so they don't pull unequally on the electrons. In other words, nobody wins. So what they do is they share those 2 electrons and it forms a bond. So you have a diatomic hydrogen molecule. Let's see, somebody else showed up. Yes, hold on a second. I want to be sure I get everybody credited with attending. All right. And there's another one that sounds like. Well, oops, sorry. I'm scrolling the wrong thing. So how many do I have? 1, 2, 3, 4, 5, 6. So I'm missing one. Ah, okay. Gotcha. All right. So this pattern is repeated, particularly for the diatomic elements. Remember, I had you memorize those: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomics, and they form those diatomics by sharing electrons. Right? That's the only way they can do it, because they're not unequally attractive for electrons. They can't form ionics. So you'd have something like nitrogen, which would actually share three electrons each. Right? So you'd have a bond here, you have a bond here, and you have a bond here. That's what one line means: 2 electrons to form the bond. Now, why did they do that? Well, in general terms, bonds form because the product of the bonding is at a lower energy than the separate atoms. Okay, so these two up there would be at a certain energy level, right? But these would be at a lower energy level. Okay, that drives the formation of bonds. Is the before and after energy profile. If it's lower energy after, then the bonding is favored. It increases stability. Okay. So there's another reason that the sharing takes place. Remember when we drew electronic configurations, right? For hydrogen, you would have a 1s1. I'm sure we did that, didn't we? We've done electronic configurations, correct? I don't want to talk about something we haven't covered yet. No, no response. Let me take a look at my syllabus and be sure. Because if I rattle on about something you've not been introduced to, then yeah, atomic structure. Okay. Yeah, we have talked about electronic configuration. So hydrogen would be a 1s1. The next one up is helium, right? So helium has 2 protons and 2 electrons. So it would be a 1s2. Right? So what does that mean? That means that s orbital is full. Can't get any more electrons in there. And that's otherwise known as a happy state, right? When you can fill an orbital, the orbital itself is happy. Well, what happens is, by combining this one with this one, and we share electrons, this one thinks it has a complete 1s2, and this one thinks it has a complete 1s2. So they're tending toward noble gas configuration. this also works for other bonding situations where you're looking for, see, the next group up would be neon, right? So what would oxygen be? Oxygen has 8 electrons. So it'd be a 1s2, 2s2, and a 2p4. Okay? So how many electrons does oxygen need to look like neon? Neon is 10. So it would be a 2p6. Right? Oxygen needs 2 more electrons. So if it bonds with another oxygen, which also has the 2 electron need, then they would share 2 of these electrons. Right? You'd have like that, 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 and that. So they would share these 2 electrons with the next oxygen over here. And it would have like that. And they would share those 4 electrons and make 2 bonds. And that would make this oxygen think it's a neon, and this one thinks it's a neon. So they're tending toward that noble gas configuration. And that's why when you get 2 oxygens together, they form 2 bonds between them. Okay. And just to reiterate, the electrons that are participating in this bonding scenario are always valence electrons. In other words, they're in the highest energy orbital. So this 2, these right here, those are valence electrons, right? 6 electrons. And how many does it take to make a full second level? Means 8, right? The octet rule needs 8. So that means oxygen can form 2 bonds, right? And with another oxygen, it does that with the other oxygen because it needs 2 bonds also. But for something like water, oxygen needs 2 electrons. It gets 1 from this hydrogen and 1 from that hydrogen. The hydrogen can't form with just 1 bond, right? So it takes 2 of them to satisfy oxygen in this situation. And then hydrogen also gets something out of the deal. It gets a shared electron from oxygen, makes it look like helium. And oxygen thinks it's neon. Okay, so that tendency toward the noble gas configuration is a driving force for bonding. Let's see, I'm drifting. There we go. All right. I've already said this, actually. When we show the bond as a dash, that is equal to 2 electrons. If you need to share another 2 electrons, then you draw another line for another bond. Thus, you have the potential for single bonds, double bonds, triple bonds. I've never seen any quadruple bonds, but I think they do exist in exotic situations. But for our purposes, single, double, triple, that covers everything. And notice that what we've got here is a Lewis dot structure. I'm pretty sure we covered that also in the previous chapter. In fact, chapter 4 is where we got that. So you draw the Lewis dot structure, and it helps you understand what electrons are available for bonding. Right? So fluorine, if you draw the Lewis dot structure for fluorine, How many valence electrons do you have? Well, you count over from the left. 7 positions from the left on the periodic table means that you have 7 valence electrons. Okay? So that means we have 1 electron available for bonding. Plus, if you add another electron in here from some other source, you get a noble gas configuration. Right? So where's that electron coming from? Well, it can come from anywhere. In the case there, what we have is hydrogen. Hydrogen supplied that extra electron. Now we have a single bond between fluorine and hydrogen. If you instead have another fluorine molecule, then you can get the 1 electron from one and 1 from the other, and you form a single bond there also. And fluorine now thinks it looks like neon. Right? So if you did it with bromine, what would it look like? We just look at your chart, right? Where's bromine? Bromine's right here. Right? How many? 1 electron will make it look like what? Krypton. That's why all the halogens tend to form single bonds, because they only have 1 electron to share. Or if they're involved in an ionic bonding situation, they would accept 1 electron. So if you have sodium, which has 1 valence electron, right? It's a 3s1, and you form a bond with bromine. Well, bromine has like that, right? So what happens? Well, the halogens attract electrons much more strongly than the alkali metals. So this electron is transferred over here. That gives it a negative charge. That makes this one deficient in 1 electron, makes a positive charge. Now you get the ionic bonding. But by transferring that electron over here, bromine looks like krypton, and sodium loses 1, so you go backwards, and it looks like neon. Okay? So for either the ionic bonding situation or the covalent bonding situation, you have a tendency toward noble gas configuration. Okay. So those paired electrons, in this case, we're showing around fluorine. Those are non-bonding electrons. They might be valence electrons, but they don't participate in the bond. They're often called, the ones that they're non-bonding, the ones that bond are often called, no, the ones that are non-bonding, that are paired together, are called lone electron pairs, lone pairs. You see those in the water molecule. Like that. So you have those 2 lone pairs around the oxygen, and then you have, so how many are actually participating in the bonding? In the 2p orbital, you have 1 here, 1 here, so that's 2, 4, 6. So you have 6 electrons, which would be the valence electrons. And these are lone pairs up here, right? They're not significant for the bonding, but they are significant for another topic that we're going to cover before this, at the end of the chapter. Okay. What's the difference between bonding electrons and lone pair electrons? The bonding electrons are valence electrons that are shared between atoms. And I might add, they may even be transferred if it's an ionic bonding situation. But for the covalent bonding, they're shared, and the lone pairs are non-bonding. Okay, this is a single covalent bond, just one line. Two electrons between the two hydrogen atoms are shared. And this makes an H2 molecule. Carbon dioxide, in this case, we have two pairs on either side. So what does that mean? That means that carbon had 4 available electrons for bonding, whereas oxygen only had 2, right? So oxygen can form 2 bonds, carbon can form 4 bonds, and it does so with these 2 oxygens. Nitrogen, right, showed you that one earlier. You've got 3 electron pairs here, 3 electrons from one nitrogen, 3 from the other, forming 3 bonds, 6 electrons. All right, so for a double bond, you have 4 electrons shared. For a single bond, you have 2. For a triple bond, you have 6. All right. So it's helpful to recognize how many bonds each element is capable of forming. Right? And if you work backwards from the right-hand side of the periodic table, you find that the halogens are capable of forming a single bond, whereas the chalcogens are capable of 2 bonds because they have those 2 unpaired electrons. Nitrogens, pnictogens group, they have the potential for 3 bonds because they have 3 unpaired electrons. And the carbon group tends to have the ability to form 4 bonds. Okay? By the time you get to the other side, now you're talking about metals. And metals, well, metals do form bonds with metals, but it's a special animal that we're not going to talk about today. It's called the metallic bond. Okay, so if you recognize how many potential bonds each one of these groups can form, it makes writing the compounds a little easier and more intuitive, in fact. So oxygen could form 2 single bonds or 1 double bond, right? So you have 1 atom up here and 1 atom over there, or you have an atom over here that is also capable of forming 2. If that's another oxygen atom, then, problem solved. If it's a nitrogen atom, then you have a situation of, right, the nitrogen, if it only forms a double bond, then you've got an unpaired electron. And what do we call that? Any species with an unpaired electron is a free radical. Free radicals are extremely reactive. In fact, you may hear in the popular literature somebody trying to sell you a product that you take as a dietary supplement. And its claim to fame is it will scavenge free radicals. And that's not entirely false. Your body does, in the process of these biochemical reactions, produce a significant number of free radicals. And those free radicals are reactive and they can damage parts of the cell. So if you can scoop those free radicals up before they have a chance to do any damage, then you should be healthier. And that's one of the reasons behind mega doses of vitamin C. The famous chemist Linus Pauling was noted for massive overdoses of vitamin C because he believed in that free radical scavenging. Okay, nitrogen can form 3 bonds, right? It can form 3 single bonds. It could be a double and a single, or it could be 1 triple bond. There are examples of that type of molecular structure with nitrogen all over the place. If it had hydrogen here, we have 3 hydrogens, you'd have ammonia. Okay? And carbon can form 4 bonds. Okay. So there's a special type of covalent bond, and we'll just mention this. It's called a coordinate covalent bond. The coordinate covalent bond, we've studied up to this point and been introduced to sharing electrons. So if you have a single bond, you get 1 electron from one atom and 1 electron from the other, they share, right? But sometimes one side contributes everything for the bonding. So there has to be an advantage to doing that. Otherwise, it wouldn't give them up. So this coordinate covalent bond is formed when one atom provides both electrons for the bond. Here's an example. Right, if we have this molecule, ClOH, right? But it would prefer to add another oxygen, right? So it would add an oxygen in here. No, it would be attached to the chlorine. Right? So how does it do it? Well, if you'll notice, this chlorine has a complete octet. In other words, 2 electrons from the bond are shared, and then these paired electrons all around the outside. Right? So that chlorine has all the electrons it needs. But it also has a tendency to form another bond. In other words, if it bonds with oxygen, the energy state for the molecule afterwards is lower, right? So that's the driving force here. So what happens? Well, oxygen needs 2 electrons. This oxygen needs 2 electrons, right? It has, 6 in its outer shell. Right? Normally what it would do would, with one of these pairs here, would be split up, and you'd have a lone electron here and a lone electron there. But in this case, chlorine is supplying both electrons to bond with those 2. So the bonding pair of electrons is contributed by chlorine only. Oxygen doesn't contribute any electrons to this bonding. That's a coordinate covalent bond. Now, the thing about it is, after the bond is formed, all electrons are equal. You don't know where the electrons came from. So this is really a theory that provides an explanation for the bonding process. It's not something that we've directly, well, maybe they've directly observed it, but I haven't read any information on that. But it still remains that once the bond is formed, the electron pair, who knows? We don't know where it came from. The only way you can tell that it's a coordinate covalent bond is that before you have this situation and after you have this situation. And the only way that can happen, because there are no unpaired electrons around that chlorine, the only way that that bond can form is if chlorine donates both electrons. Okay. This is just an illustration of what a regular covalent single bond would be compared to a coordinate covalent bond. And it just says in pictures what I said in words just now. All right. I already said that. And in order to form this coordinate covalent bond, the atoms participating have to deviate from what they would normally experience in a bonding situation. Right? Chlorine, in that earlier example, I mean, it doesn't have to, bond to form a complete octet. Oxygen does need to bond. Right? So the overall energy before the reaction is higher than the energy after the reaction. And you have the bond is formed. Similarly, nitrous oxide, right? Laughing gas, N2O. That molecule would normally not form, except under coordinate covalent bonding situation. Similarly, carbon monoxide would not form. Now, once the bonds are formed, you still have an octet around each atom, right? Around this oxygen here, you've got 2, 4, 6, 8, right? One line means 2 electrons. And around this nitrogen, you have 2, 4, 6, 8, right? That's good. And around this nitrogen, you have 2, 4, 6, 8, right? So they're all happy. They've all got octets. Similarly with carbon monoxide, 2, 4, 6, 8, 2, 4, 6, 8. Both carbon and oxygen have their octets. All right. So we mentioned earlier in the previous chapter how to write a Lewis dot structure for an atom. Right? You just take the valence electrons and position them around the atom. You do one dot at a time in the 4 places, like oxygen, right? Then you've got 2 more electrons that have to be positioned. Then you start pairing them up. And that will be a Lewis dot structure for that atom. But the use of the Lewis dot structure doesn't stop there. We can write Lewis structures for molecules as well. And the example here is SO2. So the starting position is you have to know that you've got a valid molecule, right? This SO2. That's a valid molecule, right? Our starting position, it has to be valid. We know it exists, okay? Then you go into each one of these and count up the valence electrons. And to do that, you just count from the left on your periodic table, right? So sulfur and oxygen are both 6 positions over from the left. So sulfur contributes 6 electrons. And each one of these oxygens contributes 6 electrons. So you have a total of 18 electrons. All right? That's their starting position. Total of 18 electrons contributed, valence electrons contributed by the atoms in the molecule. Okay? Then you you form a single bond. In this case, sulfur's in the middle, oxygens are peripheral. Now, how do we know that? In general, the atoms that are, you compare the positions of the atoms in the periodic table. And the ones to the left and below go in the middle. Right? So sulfur is below oxygen, it goes in the middle. You can also deduce that from the way the compound is written as well. Sulfur would tend to be bound to 2 oxygens. Rather than saying something like this, sulfur goes in the middle. All right, so how many electrons did we use up in order to form those bonds? 2, 4. We used 4 electrons. So we subtract those, and we have 14 electrons left. Okay, Now we have to position those 14 electrons in that molecule. So you work your way from the outside in. So we would go 1, 2, 3, 4, 5, 6. Then we can start pairing. 7, 8, 9, 10, 11, 12. At that point, oxygen is complete. It has 8 electrons. 2, 4, 6, 8. So we used up 2, 4, 6, 8, 10, 12. We used up 12. That means we have 2 electrons left over. We're working our way from the outside in. That means those other 2 electrons have to go on the sulfur. And we could put them, we could pair them, doesn't matter. So now we've used up all of our valence electrons. Okay? All right, so that one says, there we go. There's our extra pair of electrons right there. Now, you try to make octets around everything, right? Oxygens already have octets. Sulfur doesn't have an octet yet. 2, 4, 6. It only has 6 electrons. So how do you resolve that issue? Well, one way to do it is to make a double bond, right? Add a bond somewhere. So if we don't need to take electrons from oxygen because it's complete. But we do have these 2 electrons here, right there and there. We could put those into a double bond right here. And then we've used up those electrons. So now what do we have? Well, at this point, we have a molecule that looks like this. Oops. No, that's not right. I'm sorry, that's not right. Because what would happen, right? It wouldn't do sulfur any good. I mean, it still has 6 electrons. But it would make oxygen exceed the octet. So we will have to take electrons from an oxygen. So if we take these 2, go over here, now, and let's pair these up. Now we have a double bond here, and those are gone. So now we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, so now we have this one, that one, and there. All right, now that satisfies the octet. But just to point out something that's might be obvious, why did we come from this oxygen? Why didn't we come from the other oxygen? We could have come from the other oxygen, and it would have made this one. Right? So they're equivalent Lewis structures. They're perfectly valid, both of them. So how do we deal with that? I mean, which one is right? They're both right, right? So we're going to introduce a concept later called resonance. So what happens is, using this model, we have no choice but to accept both of them. And they just sort of jiggle back and forth between the 2. Now, that's not really what happened, but the model that we've chosen to draw these structures limits our ability to go anywhere else. We have to do it that way. There's no other choice. At least not with this theory. All right. So let's look at some other possibilities. Hydrogen ought to be easy because there's only one electron each, right? And for hydrogen, we're not obeying the octet rule, we're obeying the duet rule. Hydrogen and helium have special, they're duets because there's only one, there's the 1s orbital and that's it, right? You can't go to 8 because you don't have enough energy levels. But fluorine, we can form this type of structure, right? Only one bond between them. Now each one thinks it has an octet. So hydrogen has a duet, fluorine has an octet, they're happy. How about ammonia? Right? Remember, ammonia forms 3 bonds, right? So hydrogen forms 1 bond each, ammonia gets its 3 bonds, it's 2, 4, 6, 8. There you go. Carbon dioxide, draw the Lewis structure for that. You get a double bond between here. Why is that? Because when we positioned all of those electrons around the oxygens had an octet and carbon was deficient. So we took 2 electrons from one oxygen and 2 electrons from the other, formed these extra bonds. Now carbon has an octet and oxygen still has its octet. Carbon tetrachloride. Notice that all the octets are complete and carbon has 4 bonds. Okay, the total number of dots in the Lewis structure for SO2, the total number of dots is equal to the original count of valence electrons, right? 18, right? 18 electrons. That's all you have to work with. Now, when you start counting octets, then each one thinks it has an octet. So the tendency there is to say that we have 3 atoms with an octet each. 3 times 8 is 24. But we don't have that many electrons. We're sharing electrons to make the octets, and we only have 18 electrons to share. All right, so now we're going to diverge a little bit and talk about polyatomic ions. We mentioned them in chapter 4 because in order to form the type 1 and type 2 compounds, polyatomics are discrete ions. They're molecules. In fact, the polyatomic ion is a covalently bound molecule that happens to have a charge. So let's take an example. Let's take the one cation in that whole list and look at it. Okay? So how would we draw that Lewis dot structure for ammonium? Well, we have nitrogen, which is 5 electrons, and hydrogen, which is 4 electrons. But we've got a plus charge. So that means that we are actually deficient in 1 electron. So we would expect to have 9 electrons, but we really only have 8. Right? So we have 8 electrons to position. Right? 2, 4, 6, 8. We're done. That is the Lewis dot structure for ammonium. And whenever you're drawing a Lewis structure for an ion, you have to include the charge. So we put it on the outside of the brackets. Okay, you can do that for any one of the polyatomic ions. Right, the all the rest of them, of course, are anions. So when you count up the electrons, if it's got a charge, then you add an electron equivalent to that charge, right? For NO3, right, you would have 5 here, and you would have 3 times 6 would be 18 plus 1, right? So you need that many electrons to position in your Lewis structure for nitrate ion. Okay? So here's an example. The correct structure for sulfate looks like that, right? Sulfur is in the chalcogen group, like oxygen. So what's odd about that? Well, the odd thing about that is oxygen tends to form 2 bonds. Whereas in this case, sulfur is forming 4 bonds, right? So that helpful rule doesn't always apply. But when we write the structure, this is what we get with the 2- charge. And then the ionic bonding occurs between the covalent polyatomic ion and the cations, the potassiums, right? You wouldn't write it this way because that implies a covalent bond. They're not covalent bonds for potassium and the polyatomic ion. Those are ionic. So we have a combination here. We've got the internal structure of the polyatomic is covalent, and then the bonding between that ion and the cations is the other part of the structure. Okay. How many valence electrons are present in the polyatomic ion? So you just add them up. Sulfur's going to have 6. Oxygen's going to have 6 each. So that's actually 5 times 6 is 30, plus 2 is 32. Right? So you have 32 electrons, and you count them up: 2, 4, 6, 8. 8 times 4 is 32. So all electrons are present and accounted for. All right, let's see. Let me get my hard copy out here so I can keep track of what I'm doing. Okay. Yeah. Now, we're going to talk about geometry. In order to determine, now I can't remember if we talked about polar molecules yet, so I'll just reiterate. A molecule that is polar has a slight electron density increase on one side of the molecule and a decrease on the other side. So it's not evenly distributed electron density. Example. Okay. This is obviously a polar molecule, which means that the electron density tends toward the fluorine. It's not just because it has all these lone pairs out here, but because the bond is also polar. It tends to draw these electrons here over there like that. Like most of the electron density is with the fluorine. It's a very polar molecule. And we designate that first by saying this versus that. That small d, the delta, the Greek delta, means a slight charge, not a complete charge. If it's a complete charge, you just write the charge. So it's a slight redistribution of electron density toward the fluorine. Okay? So that means the polarity of the molecule is negative this way and positive that way. What does that mean? Well, if you only have hydrogen fluoride in the gas, then they will orient themselves so that the neighbors have positives on this side, right? So they can form that, it's rather a weak bond, but it's still a bond between the molecules. Another way to designate it is to draw a line with an arrowhead and a plus on the end that's toward the delta plus, and the arrowhead is toward the delta minus. This is known as a dipole moment, and moment is derived from physics. So the dipole moment is negative toward the fluorine. That's how we write it. All right, so in this case, we only have 2 atoms in the molecule, right? So what's the structure here? Well, it's linear. It goes straight like that. And that's obvious because there are only 2 of them, right? Can't be anything else. But there are 2 factors that contribute to the polarity of a molecule. One is the polarity of the bonds. Are the bonds polar? Right? So you got to have polarity of the bonds, right? If these were 2 nitrogens, that would be nonpolar, right? Because nitrogen is pulling equally on both sides. The electron density is equally distributed. So that would be a nonpolar molecule. Oxygen's the same way. Hydrogen's the same way. All the diatomics are the same way. Or if you have 2 atoms bound together that have roughly equivalent attractiveness, right, toward the molecules, then toward each other, then you get an even distribution of electron density, and that molecule is nonpolar. But if you have polar bonds, then the other question is, what's the geometry? Because if you have something like this, oxygen pulls more strongly. And the word for that is electronegative. Oxygen is more electronegative than carbon. So it pulls that way. But this one pulls this way. So what do you get? Well, you still get some polarity in the bonds, but overall the molecule is nonpolar because they're pulling in opposite directions with equal strength. So they cancel one another out. So the second condition is geometry. This molecule is linear. So those polarities cancel one another out. For an example like water, which is like this, the polarity is this way toward the oxygen. So when you sum those vectors up, that's what we call them, you do a vector summation of those arrows, you get one like this for the entire molecule. So that's why water is polar, because it's bent. And the polarity of the OH bonds do not cancel one another out, they actually add. Right? So the polarity of the bond and the geometry determine the polarity of the molecule. All right, so here's the theory that we're using to govern this. And actually, Vsepr, and I'll explain that in a minute. Vsepr is a subset it's a subset of the localized electron model. So Vsepr. This is valence, shell, electron, pair, repulsion. Vsepr. Now, I take issue with this electron pair because the way the model is used, we're actually talking about electron groups. And that'll become obvious in just a minute. I'll explain that to you. But that's the acronym, and it's stuck, and we have to use it. So the Vsepr model speaks to the issue of geometry, and it determines geometry around a central atom based upon the electron pairs. Electron pairs positioned around the atom try to get as far from one another as possible, right? Because they're all negatively charged, so they repel. So we position them in such a way, whether they're free lone pairs or in bonds, we position them in such a way that the repulsive forces are minimized. That is, they're far from each other as possible. And that's the basic concept for Vsepr. Maximum separation of the electrons and their groups. Okay, when we talk about the Vsepr and the geometry, we're always focused on a central atom. Now, if the molecule is really simple, then you only have one central atom. Like water, oxygen would be the central atom. Or carbon dioxide, carbon would be the central atom. What's the geometry around that central atom? When you get to more complex molecules, very large molecules, then you have geometries around the numerous atoms, right? This atom might be a linear geometry around it, while this one over here in the same molecule might be a tetrahedral. You might have 4 attachments to it. But for simple atoms, for simple molecules, there's only one central atom, and we'll try to keep it that way as much as possible for this level of chemistry. Okay, so here's a statement on what I consider to be valid. Instead of electron pair repulsion, it's electron group repulsion. Right? So if you have lone pairs, yeah, they act like independent pairs. That's true. But if you have electrons in a bonding situation, then a single, a double, a triple bond, they're all equivalent, treated in this theory. And I'll show you an example that makes more sense than trying to explain it. So what are the steps? First of all, you need a Lewis dot structure for your molecule. That's essential. If you can't write that, then you're dead in the water. Then you take that Lewis dot structure and you determine the number of groups surrounding the central atom. And once you do that, then you say, how can those groups be positioned for minimized repulsion? And that way you predict, initially, you predict the electronic structure of the molecule. Right? Because if you have non-bonding pairs, that's not really the molecular structure, right? Because you can only see whole atoms. But you have to go through that step. You need the electron group geometry first. Then you can imply the molecular geometry from that. Okay, so what we need is an example. Okay, here we've got carbon dioxide, and we've written the Lewis dot structure, right? So how many groups are around the carbon? 2. So that means the only possibility here, we've got 2 electron groups and no lone pairs. The only possibility for that structure is linear, from here to here to here, right? That makes a maximum separation of electrons in these bonds, 180 degrees apart, right? It wouldn't make any sense to make a bent molecule out of that, right? To put oxygen down here and oxygen down here, because that would bring the electron groups closer together. And that defeats the whole purpose of the theory. How about this one? The central atom here is carbon. You got an electron pair over here in a bond, and you got 3 of them over here. For all intents and purposes, and for the model, they're equivalent. So you have, again, a situation where you have a linear structure from hydrogen to the central atom to nitrogen. Okay? Now for this situation, if we draw the Lewis dot structure for formaldehyde, H2CO, we find that we have a double bond with oxygen, single bonds with hydrogen, and around the central atom, you have 3 pairs, 3 groups, excuse me, 3 groups of electrons. The most efficient separation for those groups is a triangular, an isosceles triangle in the same plane. So that's why we say trigonal planar, right? And since there are no lone pairs around carbon, that electronic structure is also the molecular structure. It's only when you have lone pairs around that central atom that you have a deviation from, you have a difference between electronic structure and molecular structure. And here's an example, right? If we draw sulfur dioxide, we get this structure, right? Oxygen's got its octet here and here. Sulfur has an octet, 2, 4, 6, 8 in a lone pair, right? So that non-bonding electron pair enters into the electronic structure configuration. So we have that one, this one, this one, that's 3, which is trigonal planar electronic structure. Now, if you cover up that or ignore that lone pair, what do you have left for the molecular structure? Well, they're still in the same position, but now you're ignoring that, and what you have now is a bent molecule. I think your authors in the book call it angular. I think bent makes more sense. But there's one where there's a difference between the electronic structure and the molecular structure. Okay. Here's an example where you have 4 groups bound to the central atom. The most efficient positioning for these groups is in a tetrahedron, right? A triangular-based pyramid, right? So here's the base of the pyramid here, and there's the apex. That forms a tetrahedron. Do the same thing with ammonia, only in ammonia's case, you have a lone pair. So you have an electronic tetrahedron, but you have a trigonal pyramid with this triangular base and the nitrogen at the apex for the molecular structure. All right. Another example, oxygen and hydrogen form water. You have these 2 plus these 2 to deduce the electronic structure. And the electronic structure here would be also tetrahedral. But if we ignore the lone pairs, what do we have? A bent molecule. That's why I always draw water with that bent structure. Okay, so what does that mean for the bond angles, right? If we go back, let's see, the bond angle here, of course, is 180 degrees, and that's around the central atom. The bond angle here, from there to there to there, this angle right in here is 60 degrees, right? No, 120, excuse me. If I were internal angles of an isosceles triangle are 60, but the bond angle here is 120 because what? Go all the way around, it has to be 360, right? So you got this angle plus this angle plus this angle has to be 360. So 360 divided by 3 is 120. So that angle is 120 degrees. Now, theoretically, this angle would also be 120 degrees. The problem is lone pair electrons that are not bound, are not confined in a bond, tend to balloon. Right? So that's what we've shown here. These electrons are ballooned out, and what they do is they spread their charge out over more area, and there's pressure on this bond angle, right, pushing down here. So these two bonds are pushed a little closer together than 120. They might be, I don't know, 115, 110, something like that. Theoretically, it'd be 120, but it's usually a little less when you have this lone pair pressing down on the outside. Similarly, what would be the bond angle in a tetrahedral situation? You just have to memorize this one because it's not easy to calculate. That bond angle is 109.5 degrees. So if it's a perfect tetrahedron, molecular structure, this angle will be 109.5 degrees, right? And this is methane. The methane gas has that structure. Now, we would expect these angles to be 109.5, except they've got the lone pair pushing down. So they'd be less than 109.5. I don't know what, but less. Here you've got two lone pairs pushing, right? So that bond angle will be even less than 109.5 than the ammonia molecule would be, because you've got these two ballooned out pushing down on those two bonded pairs. All right. So here's a situation where you have two central atoms, more than one central atom, right? For this one, this is acetylene, right? So what's the VSEPR says there's one around here, 1, 2 around this one, so that's linear. So that bond angle is 180 degrees. Same thing over here is 180 degrees, right? This one is tetrahedral electronic structure. This is hydrogen peroxide. So you have these two lone pairs plus these two bonds. So you have a tetrahedral electronic structure here and another one here. And then when you look for the molecular structure, you get a bent molecule. So the hydrogen peroxide would be like this. To maximize the separation of electron pairs, right? You'd have electron pairs up here, and then you have electron pairs down here. Maximum separation. For hydrogen azide, right, you have 1, 2, 3 around this nitrogen, which is trigonal planar, but if you cover this up, that makes it bent. Whereas this one has no lone pairs, so its two pairs make it linear, and it stays linear. So that one would look like actually it would look like this. This would be linear, 180 degrees. And this one would actually be 1, 2, 3 hydrogen. this would be 120 degrees because it's trigonal planar. Okay, am I out of time already? No, I've got 40 minutes. We just lost some people is all. And then the molecular structure would be bent here. This would still be linear, but this would be bent for the molecular structure. Okay. So here is, I don't remember where I got this one. If it came out of your book, I try to extract these pictures from the students' textbook so they look familiar. But this is what the electronic structure would be if you have this many electron pairs or electron groups, right? 2 means linear, 3 means trigonal planar, 4 means tetrahedral. We didn't get to 5, but when you have 5, the best positioning is 3 in a plane here, and then 1 on this apex and 1 on that apex, which means trigonal bipyramid. And then 6, we're going to stop at 6. If you have 6 groups around the central atom, then you have an octahedron, right? 4 in this plane, 1 at each apex. And now what are the bonds? Well, we talked about the bond angles here. Right? How about the angles here? Well, you have a combination of 120 degrees in the plane, and then you have 90 degrees between apex and any one in the plane. But there's one that they always leave out. How about the bond angle between this one and that one? That's 180 degrees, right? So you have 3 bond angles, 90, 120, 180. For this one, you have 90 possibility here, you have 90 here, and then you have 180 there. So the 2 bond angles present there are 90 and 180. Okay, now if all of these positions are occupied by atoms, right, then the electronic structure and the molecular structure are equivalent. So you have a linear molecule here, a trigonal there, tetrahedral here, trigonal bipyramid here, and a tetrahedron there. And this just shows you what happens in this case where you have a tetrahedron and you lose one. If you lose one atom here, then you get a trigonal pyramid. If you lose 2, you get a bent molecule. For this example, we have a trigonal bipyramid, right? 3 in the plane and 2 apex. If you remove one, the most efficient arrangement then is called the seesaw, right? Just turn it on its side. There's the base of the seesaw, and here's the board. If 2 of them are missing, then we tend to get a T-shape. That positions everybody the furthest from one another. Actually, there's an argument to be made for instead of taking these 2 away, take the 2 apexes away, and you have a trigonal planar. But this is what the textbook says. Who am I to argue? Now, if we have 3, there's no argument with the one where you have 3 missing. Right? If you have 3 lone pairs and you have 2 atoms, then the best way to position those is linear, as far apart as possible. The reason I take issue with this one is that's a 90-degree angle here and here. Why not put them in the plane? And that means everybody's 120 degrees apart. That makes more sense to me. But it may have something to do with these lone pairs ballooning things out. But if the lone pairs are at the apex, problem solved. So I would tend to say, rather than T-shape, I would say trigonal planar would be better. Okay, let's see. How am I doing? Am I even getting close to the end? We've still got to talk about electronegativity. I mentioned electronegativity and bond polarity, so we should be able to get through that fairly quickly. But if we determine the shape of each one of these, we find that this one is linear because there are no lone pairs. So the molecular and the electronic structure are identical. This one we looked at earlier. This one's a trigonal pyramid. And rather than 109.5 degrees, which it would be if all positions were occupied by atoms, then that lone pair compresses the bond from 109.5 down to 107. Ozone. Ozone is 3 oxygen atoms bound together, and the central atom is surrounded by 2 electrons, 2 electron pairs. So the molecule becomes bent. Okay. Electronegativity. Electronegativity is a concept that was, if not introduced, developed pretty well by Linus Pauling. And it was designed to help understand how atoms associate themselves in a molecule, and how the electrons distribute themselves in that association. It also helps understand the character of a bond. We mentioned earlier oh, by the way, the localized electron model is just that. What it says is that in any bonding situation, the electrons are assigned to an atom. They're localized to the atom. Either they're lone pairs or they're shared between atoms. But the atoms still retain their identity and their orbital structure. So you overlap atomic orbitals to get your bonds. Okay, so that's the localized electron model. And now we're back to electronegativity. You can have ionic bonds right here. And then you can have covalent bonds. So you have complete sharing over here, 100%. And here you have 100% ions. Okay? But as is so often the case, there's a continuum between the two. So you could have a bond that forms that's mostly covalent, but it still has some ionic character. It could be 80% covalent, which means it's 20% ionic. Or you could have a similar situation over here. It could be 20% ionic, but it still has some, 80%. 80% ionic. It still could have some 20% covalent character. Right? So it's like I've said before, nature just does what it does. We invent these theories to try to wrap our heads around what's actually happening. And when we talk about covalent versus ionic character, there's a distribution, right? It could be right in the middle. It could be 50-50. And one of the ways to understand that is with the concept of electronegativity. If the atoms are equally electronegative, like 2 oxygen atoms bound together in a diatomic molecule, there's nobody winning. So the bond character is a 100% covalent. Right? If you have 2 that are bond like nitrogen and oxygen, there's slight difference, right? It's mostly covalent, but there's some ionic character, and you judge that ionic character based upon the difference in electronegativity between the nitrogen and the oxygen. was, I can't use that one. That blue doesn't want to erase. Let me pick an unused black one here. Okay, now on the periodic table, fortunately, the way it's arranged, the electronegativity, or the strength of attraction, has values. And there are several systems, but one system, and one of the most popular systems, is the upper right-hand corner, where fluorine resides, is the strongest electronegative element in the chart. We don't include the noble gases because they're happy the way they are. They could care less what the rest of the chart does. So we stop with fluorine. Fluorine has a 4.0 electronegativity. The lowest electronegativity is lower left. In this region, it's like less than 1. So from lower left to upper right, we have an increasing electronegativity. What does that mean for periods and families or groups? Well, the group electronegativity increases as you go up a group. And the electronegativity increases as you go across a period. That's why lower left to upper right is the trend, increasing electronegativity. So what does that mean for bonding? Well, if the difference in electronegativity is sufficient, then you have an ionic character bond. So that's why metals with their low electronegativity combined with a nonmetal with its higher electronegativity tend to transfer the electrons from the metal to the nonmetal because of that strong pull. So here's an example. Rubidium, 0.8. It has a very low attraction for its valence electron, whereas fluorine has a very high attraction. Right? And notice as you go to the left, decrease, 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 decrease. Now hydrogen's stuck over here by itself. Hydrogen fits right in here around boron. We just put it over there because it balances the chart. Okay. So like I said, this is the Pauling scale. And there's a mathematical formula that's used to calculate these values. I mean, Pauling didn't just pull this out of thin air. He used experimental data to inform his, help him develop his formula for the calculation. We're not going to do that, of course. So with this general trend increasing from lower left to upper right, what's the explanation? Right? Well, we'd have to stay within a group or within a period to make any sense of it. So if we go from left to right, we're in a period. So what's happening from left to right? You're increasing the number of protons, right? But how about the energy levels of your valence electrons? Well, you're adding electrons, but you're not changing their energy level. So actually, you're increasing the positive attractive force in the nucleus. And what it's doing is it's actually shrinking the size of the atom. It's pulling stronger because of those extra protons. Now there's an effect that occurs. The lower level non-valence electrons offer some shielding. They sort of suck up the positive charge with their negativity. But as you go from left to right, you're not changing those core electrons. You're only changing the outer electrons. And they're in that same same energy shell, and you're increasing the number of protons. So from left to right, you're increasing the number of protons, which increases the effective nuclear charge, is what we call it. The effective nuclear charge, which is positive, is the explanation within a period for an increase in electronegativity from left to right. You're adding more protons. From top to bottom, If you go down a group, what's happening? Well, you may be increasing protons, of course, but you're also increasing the size of the atom. And you're adding more electrons in lower energy levels. So you're moving the valence electrons further away from the nucleus, which means they don't feel the attraction from the nucleus. You're actually decreasing the effective nuclear charge as you go down a group. Okay, so both of those combined give us that trend from lower left to upper right, increasing electronegativity. Okay, if we try to combine lithium and fluorine together, which one will have more attraction for the electron? Well, the one that's to the right and above. And in this case, lithium and fluorine are in the same period, so it's just left and right. So fluorine is farther to the right than lithium. It will have the greater attraction because it has a higher electronegative number associated with it. Okay? In a bond between fluorine and iodine, okay, so now we're changing. Fluorine and iodine can bond together, right? Which one has a stronger attraction? Now we're in a group, so we look to the one above is the higher electronegativity. And fluorine is at the top of the table. Iodine is closer to the bottom of the group, excuse me. So the stronger attraction would be toward the fluorine again. Okay, which one of these has the highest electronegativity? All right, we look at the chart, right? Where's hydrogen? Well, hydrogen should be positioned in the neighborhood of boron, right? But helium is farthest to the right, only helium doesn't care. It doesn't have a high electronegativity because it's complete. So helium's out. All noble gases are a non-issue with electronegativity. Oxygen is further to the right than hydrogen, but chlorine is below oxygen, right? So how do you break the tie? Right? Well, you look at the chart, really. Chlorine is below oxygen, even though it's to the right, it's below, which, and the increase in size and the movement down trumps the movement to the right. If it were oxygen and fluorine, fluorine would win. But it's oxygen and chlorine, and the chlorine has lost that effective nuclear charge more so than being to the right and gaining protons. That's why oxygen is higher. And if you look at the table, let's go back. Let's see. Here we go. So there's chlorine and there's oxygen. So the numbers bear out that assumption. Oxygen is more electronegative than chlorine. All right. So I mentioned earlier bond polarity, and that has everything to do with the difference in electronegativity between the two atoms that are bonded together. What is the difference in equality? Well, you take the electronegativity of one and subtract the other, and what's the difference? Well, the greater the difference, the more polar the bond. That's just the way it is. When you put two equivalent atoms together, there's equal competition. They're equal in electronegativity, so there's no winner. It's always nonpolar. When you have a difference of, let's see, what was it? 2.1 for hydrogen, and chlorine was like 3. So there, you definitely have a polar bond toward the chlorine, right? So here's our notation that I mentioned earlier, right? Slight charge toward the chlorine, slight positive charge toward the hydrogen. And then our dipole moment is expressed with this arrow and a plus on one end of it. Now, these are general rules. If the difference in electronegativity is less than 0.4, then we say the bond is essentially nonpolar. Okay? If it's between 0.4 and 1.5, then we say it's essentially a polar covalent bond. If it's between 1.5 and 2, it could be ionic. It could be more strongly polar covalent. It depends. If it's between a metal and a nonmetal, then anything over 1.5 is considered an ionic bond. But if there are two nonmetals and their difference is between 1.5 and 2, then we say that is a highly polar covalent bond. Okay. Once you're over 2.0 difference, which always means a metal and a nonmetal, then you have an ionic bond, period. There's no argument there. It's this gray area, 1.5 to 2, where you have to choose between metal nonmetal and nonmetal nonmetal bonding together. Okay. Let's see, where am I? I've still got a little ways to go. I'm going to finish today. So several people have already had to go. But as is my custom, I just keep talking. Arrange the following bonds in the descending order of polarity. That is, the first one that you put on the list is most polar. So we look at a difference. What's the difference here? Well, the nice thing about this group is fluorine is bound to each one. So all we have to do is compare the other atoms, nitrogen, oxygen, carbon, to see which one is furthest away from fluorine, right? They're all in the same period. So the one farthest to the left will form the most polar bond, right? So that's why carbon and fluorine form the most polar bond. Then the next one to the right of that is nitrogen, and the next one to the right of that is oxygen, right? So greatest, middle, least in this group. Now we've got a fly in the ointment here. We've got two fluorine compounds, but we've got oxygen here. So we have to actually compare what's the distance between the carbon and the fluorine. Well, the carbon and the fluorine is, they're 4 positions apart. They've got 2 elements between them. So that's fairly polar. How about nitrogen and oxygen? They're really close together, right? So their bond is the least polar. How about silicon and fluorine? Silicon is to the left and equivalent to the position of carbon. All right, so what does that do? That means that silicon is not only to the left, it's below. So silicon and fluorine would be a more polar bond than carbon and fluorine. So silicon fluorine first, then carbon fluorine, then nitrogen oxygen. Okay, so that took a little extra work. How about this one? Okay, this one's nice. Chlorine's bound to each one. All right, so we just need to check the others. All right, this one's easy. Chlorine, chlorine, that's nonpolar, period. So it'll be last. We just need to say, what's the comparison of boron and sulfur? Well, boron is far to the left. Sulfur is very close to chlorine. So I'd say dichlorine is last, sulfur chlorine is in the middle, and boron chlorine is the most polar. Okay, so let's see, what do we got next? Which of the following bonds would be the least polar, yet still be considered polar covalent? All right, now we have another added requirement. It has to be polar covalent to be part of the group. Then we can say which one's least polar, right? Read the question backwards. To be considered polar covalent, it can't be magnesium and oxygen. They're too far apart. Metal, nonmetal, that's ionic, right? So throw that one out, right? The least polar and still polar covalent means that if you have two nonmetals of the same element, throw that one out too, because it's not polar at all. So oxygen, oxygen, throw that one out. So now what we have to do is compare carbon oxygen, silicon oxygen, nitrogen oxygen. So which would be the most polar? Well, let's see. Carbon is 2 steps to the left of oxygen. Silicon is 2 steps and down below, so it's more polar. Nitrogen's right next door, right, to oxygen. So it's the least polar of the covalent. Silicon oxygen would have to be it, right? Cross those out, right? Oh, least polar, excuse me. I was thinking most. It helps to read the question, doesn't it? The least polar would be nitrogen, oxygen, because they are right next door neighbors. But they're still polar covalent because they're different. Like nitrogen, oxygen, different electronegativities. All right, which would be the most polar without being considered ionic. Okay, now we can cross out these two guys. And this one, I was answering the wrong question. Silicon oxygen, this is the most polar of that group. Polar covalent bond. Unequal sharing of electrons between two atoms. That's it. And the key word there is sharing. If it's not sharing, it's not covalent. And then unequal sharing is polar. Okay, so I mentioned this earlier also, the polarity of the molecule as a whole depends upon two things: polarity of its bonds and the geometry. So that's why we went through the Vsepr model. You got to know the geometry of the molecule in order to judge whether the polarity of its bonds are canceled or additive. Right, so here's our example of a molecule with polar bonds, but the overall molecule is nonpolar. Because it's linear, the polarities cancel. Now I might add, the uneven distribution of electrons is still there, right? You have more electron density here and more there. So that does modify its behavior, because you still have a slight positive charge here and a slight negative on the ends. You do get some interaction, but there is some what we call steric hindrance. In other words, these guys get in the way if another carbon dioxide molecule tried to move in here and form some sort of association between an oxygen and the carbon. But it does happen. For water, this bending makes the water molecule polar, but the hydrogen cyanide molecule, well, the hydrogen cyanide molecule is also polar, right? Because the polar bond here adds to this one and makes it polar while it's being linear, right? It doesn't have to be an odd shape. It's based purely upon its polarity of bonds. Molecule that has polar bonds will always be polar. No, I don't think so. It depends. Depends on its geometry. Okay, so in order to pull all this together, you have to draw the Lewis dot structure for your molecule. You have to determine the polarity of the bonds. Are they polar or nonpolar? Then you have to apply the molecular geometry. Three steps. Okay, that's Which of the following molecules are polar? Right? This one's polar, definitely. It's linear with a polar bond. How about this one? Well, there is a difference between nitrogen and hydrogen, and you also have a lone pair above the nitrogen. So it's slightly polar. That one is also slightly polar because it's bent and has polar bonds. But the carbon tetrachloride is nonpolar as a molecule. Even though the chlorine draws electrons more strongly than the carbon does, they're all pointing to equal directions on a tetrahedron, and they cancel one another out. All right. Which one of these is a polar compound? Well, we know that carbon dioxide is linear and its polar bonds are canceled. Beryllium chloride, how do we do that one? Well, beryllium is only going to form a bond with chlorine on one side and a bond with chlorine on the other side. It's a linear molecule, right? So it cancels out. In fact, beryllium and chlorine, that would be an ionic compound, right? So that wouldn't even qualify. It wouldn't be classified as a polar covalent compound. Water, we know, is bent and it has polar bonds, so it's polar, right? And of course, methane, CH4, is nonpolar because all of those hydrogens are pointing to tetrahedral positions. So it doesn't matter if the bonds are polar or nonpolar, they'd be canceled out anyway. Okay. Oh, we're going to name compounds. I thought I covered that already. I did in chapter 4. So this, you can consider this a review. If you have a binary molecular compound, that is nonmetals, two nonmetals that are bound together, right? What convention do we use? Well, based on what we studied in chapter 4, we use type 3 convention. You just say how much of each one there is. We follow roughly an ionic bonding character in the name, but we modify it because there are no ions in a type 3 compound. So the real trick in naming a binary molecular compound is knowing which one to put first. Because if we're going to follow the convention of ionic, we need the cation first and the anion second. So who's going to take the anion's name and who's going to take the cation position? Well, in general, it's the one with the lower electronegativity that goes first, right? That tends it toward the metallic side. So to the left and below would typically be the cation position. And then the anion position would be suffixed with an IDE, just like as if you were a type 1 or a type 2 compound. But we use numerical prefixes to name how many there are. Since there are no ions, we can't calculate how many to put in there. So we have to say how many there are. Right? So in this case, there would be carbon, 2 oxygens, dioxide. And if you look at their position on the periodic table, here, carbon's to the left of oxygen. So carbon takes the cation position and oxygen takes the anion position. Sulfur hexafluoride, right? Sulfur is to the left and below fluorine, so sulfur comes first, and we say how many, right? There's only one sulfur, so remember, we don't say mono, not for the first one. And then 6 fluorides, sulfur hexafluoride. Dinitrogen, since there are 2 nitrogens, we do say 2. Nitrogen's to the left of oxygen, so we have nitrogen, dinitrogen tetroxide. Right, and there are your Greek prefixes. Again, I think I gave those in chapter 4 also. Let's see if we follow the convention here. We did that one. Chlorine pentafluoride. Chlorine is below fluorine, right? So it'll come first. Iodine comes first, right? Phosphorus and oxygen. Phosphorus is below and to the left of oxygen, so it'll come first. And sulfur. Phosphorus is to the left of sulfur, so it comes first. So all of these follow that trend. To the left and below, the element that is in that position takes the cation position in the naming convention. Some compounds have common names. Like, we don't say dihydrogen monoxide. That's water. Hydrogen, we don't say dihydrogen dioxide. This is hydrogen peroxide, is a common name. The peroxide refers to the bonding of oxygens internally. So when we look at the structure here, that's the peroxide right there. So that common name is hydrogen peroxide. NH3 is ammonia. Into H4, we would, by convention, we would say dinitrogen tetrahydride, but that's also called hydrazine. Now, in the IUPAC naming conventions, some are considered bona fide IUPAC names, like water, ammonia, even hydrogen peroxide. Hydrazine, I'm not too sure about. That could be considered a trivial name. So if it's not a standard IUPAC name, it may have some other name, and those are called trivial names. Methane, now we're getting into a different part of IUPAC naming. Now this is organic. Ethane, that's organic. So that's a different, that's IUPAC naming, but it's not the standard format that we've used up to this point. Nitrous oxide, that's a trivial name. Dinitrogen monoxide is the accepted IUPAC name, but nitrous oxide, or laughing gas. Nitric oxide, nitric oxide, you'll see that advertised all over the place, like super beets. Super beets are supposed to boost the nitric oxide in your system for various health benefits. If you get too much nitric oxide, say if you breathe it in, of course, it can kill you because it's more active. It more actively attaches to your hemoglobin than does oxygen. Kind of like, it's not quite as bad as carbon monoxide. Carbon monoxide bonds to your hemoglobin and it won't let go. Once it's there, it stays put. So that's why it's so dangerous. Okay, which is the following compounds named incorrectly? Okay, nitrogen dioxide. That's okay. This should be diphosphorus pentoxide. Phosphorus trichloride, that's right. Sulfur trioxide, that's right. Iodine monochloride. Those are all right, except for this one. What does the penta mean? Penta means 5, right? Means 5 of something. You've heard, let's see, it's common in witchcraft to draw pentagrams. They're pentagrams. They're a gram is like a drawing. A pentagram is a 5-pointed drawing. Penta for 5. Oh, maybe I am getting close to the end. Let's see. Yeah, we're gonna have. All right. Okay. Let's say we have. I'm a little over. So if you have to go, that's okay. I'm going to finish this out because we're really close to the end. An unknown is thought to be an aqueous salt solution. However, it was determined not to be a conductor of electrical current. So we thought it was a salt solution, but if it dissolves in water and it won't conduct electricity, then it does not dissociate, which means it's non-ionic. Through analysis, it's found that the unknown contains carbon, hydrogen, chlorine in the ratio of 1 to 1 to 3. All right. So, and I assume that is atomic ratio. 1 carbon, 1 hydrogen, and 3 chlorines. Okay, that was the analysis. Which one of the following represents the Lewis structure, molecular geometry, and classification of the unknown? Right? Which one of these? Well, let's see. Do we have the right? First of all, we need to determine, is it the ratio correct? Right? 1 to 1 to 3. So 3 chlorines, 1 to 1 to 3, that's right. 1 to 1 to 3, 1 to 1 to 3, 1 to 1 to 3. Okay, so those are all valid arrangements. We have to draw the structure. Right? So we have how many for carbon? 4 electrons, 1 electron here, and then 3 times 7. So that's 21, 22, 26 electrons. So we're going to put carbon in the center. Why? We can't put hydrogen in the center because it only has 1 bond. And we got 3 chlorines, so it really would be terribly unbalanced. Besides, carbon is farther to the left than the rest of them, so it tends to be the central atom. So we have carbon, and we have a hydrogen, and then 3 chlorines. Right? 2, 4, 6, 8. Minus 8 is 18. Right? So now we put the electrons around. 2, 4, 6. 2, 4, 6. So that's 12. 2, 4, 6. So 2, 4, 6 times 3 is 18. Okay? So that's it. Right? Now, the way this is written, the bond is shown as an electron pair. So that would be an electron pair. Electron pair, electron pair. We've made the duet, the octet, octet, octet. Right. So this is correct. And let's see. C cannot be correct, right? You can't put 8 electrons around a hydrogen. So throw C out. The rest of them are correctly written Lewis dot structures, but now we need to determine the structure, right? So around this central atom, you have 4. So what does 4 mean? 4 means tetrahedron. Right? So we have a tetrahedron there. And we have an unbalanced electronegativity, right? You've got individuals here going this way, and this way, like that. And hydrogen pulling slightly, but not as strong. So the overall tends to be toward the chlorides, right? Like that. So it should be covalent compound and, well, it doesn't say anything about polarity, right? So we just say it's tetrahedral and it's covalent right here. So D would be the answer. How about this one? Let's see, get back on screen here. There we go. A liquid molecular compound is given to you and you are told to handle it with caution. Okay. What have we got here? It can cause damage or death if it is consumed in large quantities. If it enters your lungs, if you're hit with a frozen chunk of this material, or if a hot solution of it is spilled on you. So those are the conditions that can cause damage or death. But it's a covalent compound. However, the liquid is necessary to sustain life. All right, that's a dead giveaway there. Okay. The liquid is a pure molecular compound, has no taste, known to contain hydrogen and oxygen. Identify the liquid. All right. If it's essential for life and it's a liquid, there's only one possibility. It's got to be water. Besides, if you consume it in large quantities, right, that's excessive. I mean, huge amounts. It could kill you. Or if it enters your lungs, right, it can drown you. If you're hit with a frozen piece of it, like falling off a building, a chunk of ice could kill you. Or if it's boiling, it could damage you. It's a pure molecular compound, hydrogen, oxygen only. There's only one possibility. It has to be water. So we got water covered. So what is its molecular geometry? It's bent, right? We determined that, angular. And it's polar, because the individual bonds are polar, and the bent molecule makes those polar bonds additive. So the overall molecule is also polar. Okay? That's the end of this chapter. So next Friday, we'll cover chapter 6. And then the Friday after that, we'll do a review. And that probably, let's see, we're going to get the review before or after spring break. Let me check. The review comes before spring break. So that's good. That gives you all spring break to study for exam 2. That's the good news. The bad news is you've only got one exam grade that goes into your average for the midterm. And the rest is lab grades. So I'll get the labs that are turned in graded, and then between now and the midterms, you should have at least 5 labs turned in, and let me grade them to get those into your average. People tend to do better on labs. So there's a chance for you to, if you did poorly on the exam, there's a chance to bring your grade up so it's acceptable. Okay, that's it. There's nobody left in town, so I'm going to close this meeting right now.